Okay, we're continuing with number 11 through 15 in this video. Number 11, which graph best represents the vapor pressure of water as a function of temperature from 0 Celsius to 100 Celsius degrees? Now this is tricky because a lot of students who knows the Gay-Lussac's law of the gas chapter, it's easy to go with C, because another way students can reason is PV equals nRT, and then they just go, oh, the pressure and temperature are directly proportional, therefore it's gonna have a straight line like that. Well, that's a good reasoning, but that's not really answering our question. Our question said vapor pressure of water, not the gas water, so they're not the same thing. So let me show you what equation you really need to use. Well, actually, rather than the equation, the answer actually is A. This relationship was covered in the Clausius-Clapeyron equation. So let me write it for you. Clausius it's very similar to the kinetic equation, except this time instead of the activation energy, we have vapor energy, the delta H vaporization enthalpy, and then we have the R, and it's in terms of T. So for we can convert this graph to straight line by making our independent variable to be 1 over temperature in Kelvin, and on the left side we expect the ln of vapor pressure and plus ln A. That's our y-intercept in the mx, y equals mx plus b, and you expect 1 over t on the horizontal and the vertical to be ln p vapor. So again, the key word here is a vapor pressure of water, not the gas pressure. So answer is A. It's something you need to just memorize. Alright, number 12 is very tricky because it's a lab question. So let me explain that to you. The table below shows the data for 3 titrations to determine the concentration of sodium hydroxide solution with standard 0.200 molar hydrochloric acid solution using phenolphthalein as the indicator. Okay, so we are given these 3 trials, and which explanations best explain which explanation best account for the lower value of NaOH molar. So concentration of our sodium hydroxide, why is it so low in trial 3? Why is this low? To illustrate it, let me first draw the apparatus or lab setup of the titration. So you have this titrant, and you have usually you use the burette for the accurate volume, and in the titrant we have hydrochloric acid, and then we have a flask. Okay, just rough draft, and in the solution we see we have NaOH. Okay, so in aqueous solutions you expect this to be dissolved Na plus and OH minus, and as you drip this down, our volume of hydrochloric acid will decrease over time, and then at one point the color of our solution will turn colorless. So we start with pink solution, because phenolphthalein in the basic solution is pink color. So I don't have pink color in my color pen here. So just think that it's a pink color. You start with a solution in the flat pink at first, but as you add more hydrochloric acid from our burette, at one point it's gonna go clear. That's our equivalence point. Okay, so I hope that was clear what's going on. Now we need to explain why this NaOH concentration is lower than usually, as you see in trial 1 and 2. So we can kind of expect, based on the implication, that the trial 1 and trial 2 have a correct concentration, whereas we have kind of abnormal concentration in trial 3. The usual formula you use is Ma times Va equals Mb Vb. This works very well with a strong acid and base neutralization reaction. And the A here stands for the acid and the B here stands for the base. In other words, if you have like 100 mole, just arbitrary number, say you have 100 mole of H plus, then the equivalence point is you have 100 mole of OH minus. So that's what we have. Theoretically, we know because we know the concentration of sodium hydroxide is 0.223, and let's say what's supposed to be our titrant volume, and our volume of sodium hydroxide, let's say we initially measured this accurately and say this was correct. So you have 21.14 milliliter, and then let's also assume that the concentration of hydrochloric acid was accurate, so you have 0.200 molar. And then since this is our titrant, let's find the volume of this by by dividing both sides by the 0.200 molar. Then you're gonna get 23.6 milliliter of our hydrochloric acid was used up. But that's not what we see in our trial, 22.20. In other words, this sodium hydroxide was overestimated. Okay, because that was overestimated, then we should lower the we should lower the volume. Okay, in our theoretical case, our volume was overestimated, and we expect this to be lower, okay, to match our 22.20 milliliter that we observed in the experiment. So how can we explain that? One possibility is just as this shows. Maybe it was spilled, so we measure the volume of sodium hydroxide. Maybe that was correct, 21.4 milliliter. However, after you measure this, say you spilled it, okay, like something like 1.4 milliliter, say, and then when you do the titration, obviously you're gonna get less than the expected 23.6 milliliter. So these are our correct answer. Okay, I hope that was clear. Now, in case you were not so sure how D was arrived, because it had a lot of critical things in here, we can also solve this by eliminating. A. Some of the neutralized solution from trial 2 was left in the flask. Okay, when you have the neutralized solution, then it's not going to affect our MAVA and MBVB equation, so A can be crossed out. The number of drops of phenolphthalein, okay, that's independent from our equation again. Just because you drop more doesn't mean that's going to change our concentration of our analyte. And C, the hydrochloric concentration was used as 0.250 molar in the NaOH molarity calculations. Actually, if you try these calculations and say you put a 0.250, and you are not gonna get the same you're not gonna have the same equation, same calculation on the both left and right side. So C is also out. So we have to go with D. Okay, I'm gonna move to next one. Number 13. A sample of an ideal gas has a volume of 0.500 liter at 25 Celsius and 1.20 atm pressure. What is its volume at 75 Celsius and 3.6 atm? We're given the volume and we're given the temperature, we're given the pressure, and we're gonna kind of tweak our temperature and pressure, and we're supposed to find the volume. Well, you have to use the combined gas law, and that is P1 V1 over T1 equals P2 V2 over T2. Okay, we're looking for our V2. Here's something you have to be careful. The caveat is you have to change the Celsius to Kelvin. It's always that way because in the gas equations we measure it in terms of absolute temperature. So let me plug the values now. Okay, the pressure is 1.20 atm, and the volume is 0.50, 500 milliliter, over the temperature. Now here's what I was talking about, 25 Celsius. Make sure you add 273.2 Kelvin. Okay, and let's move on to our second system. We have 3.60 atm. And we have, okay, we are looking for volume. And finally, our temperature is 75 plus 273.2, and this becomes Kelvin. So I just wrote the K as a Kelvin in units. Okay, when you cross multiply and find for our V, you get 0.195 liter, and answer is B. Okay, that was easy. Number 14, in a mixture of nitrogen and oxygen gas, the mole fraction of N2 is found to be 0.700. The total pressure of the mixture is 1.42 atm. What's the partial pressure of oxygen in the mixture? Looking at this, we're given the mole fraction. The definition of the mole fraction is the moles of N2 in our case is divided by the total moles of which is our combination of moles of N2 and O2, and that turned out to be 0.700. So I'm gonna assume that's okay because this is simple ratio. Assume 10.0 moles are present in our situation. Then I'm gonna have, okay, the definition goes so that's like saying we have 7 moles of nitrogen per in the total. So how many moles of oxygen? We have 3 moles because there is no other than nitrogen and oxygen in the system here. So this is going to be important. So I'm going to write down the number of moles of nitrogen is 7 mole, and number of oxygen is 3 mole. Okay, that's because I assumed that to be 10 mole. So if you chose 1 mole, then we're going to have 0.7 moles for the nitrogen and 0.3 moles for the oxygen. And we have another piece of information, total pressure. So you need to use the Dalton's partial law equation. In other words, you can add all the partial pressures and they add up to a total pressure. So P total is 1.42. That's because the partial pressure of the oxygen and the partial pressure of the nitrogen was added. Okay, we have to find the partial pressure of oxygen. So this is what we really need, not that. Okay, now this problem has one more complication, because you need to know the relationship between the number of moles and the pressure. You have a PV equals nRT, number of moles, assuming the pressure, not pressure, volume and our temperature stay constant, only pressure and the number of moles are relevant. So if they're all static, the other three variables, then we have a direct proportional relationship between the pressure and the number of mole. In other words, if I'm to graph this, the pressure and the number of moles are going to have a straight line. So having said that, because I know that they are directly proportional, I'm going to have P of, because I'm looking for the oxygen, P of oxygen over, okay, now I want to find the nitrogen, so I can subtract nitrogen on both sides. Then I get I have to subtract the oxygen on both sides so that I get the partial pressure of nitrogen. So let me actually write that step by step. So I want to have this, the N of oxygen and the N of nitrogen. Okay, I'm going to elaborate this by writing P partial pressure of oxygen over, now I can subtract 1.42 minus PO2. That's how you get the P of N2. Then I have a single variable in the left side, but I already know the numeric value of the oxygen number of moles and the nitrogen number of moles. Okay, it was determined 3 moles over 7 moles. Okay, now let's cross multiply this. So you get 7 PO2 equals 3 times 1.42 minus P of oxygen. Okay, you can distribute these values, just simple algebra 1. Then you get what did I write? You get 4.26 minus 3PO2 equals 7PO2. You can add 3 on both sides, then you get 10PO2, that equals 4.26. So ultimately, we get the partial pressure of oxygen to be, just move the decimal point, and you get 0.426 atm. That's our final answer, and here we have nicely as in B. So the answer is B. Okay, the last problem. Okay, this problem, okay, let me read it first. The substance below have molar masses that are the same within 2 grams per mole. What they mean is the molecular mass of each of our molecules are not going to be the major factor to determine the boiling point. So the question is, what substance has the lowest boiling point? In other words, they're asking the intermolecular force. Not the intra, which is within, which is between, intermolecular force. Okay, if you took some chemistry already, you should be aware of like hydrogen bond, London dispersion force, and dipole-dipole. Okay, and also there might be some ionic and network, metallic, there are more, but we are only concerned with these 3 for now because we don't have any metals here. Okay, so looking at these choices, I know for sure that C is hydrogen bond. Why? Well, it's alcohol, ethanol. So when you have OH, like that. You get the idea. Um, Say you have water in surrounding. It doesn't have to be water. It could be either water or okay, it's intermolecular. So I'm gonna draw uh, another ethanol. Okay. What happens is there tend to be a hydrogen bond between this electronegative oxygen and the electropositive hydrogen. And you have a bunch of these millions and trillions of them in the beaker, I believe. So in the size of a beaker or anything greater. Therefore, there will be a more attraction between molecules, and to break them, it's going to require substantial boiling point or substantial heat to reach that boiling point. So definitely not C. In the same manner, we have aldehyde for our D. I know that H should be other side, but you get the idea. So again, we have the electronegative oxygen, and there can be hydrogen from another identical molecule. They can form the intermolecular force like that. So D is out. And again, we have electronegative oxygen. Despite this is not as strong as C and D, compared to A, it's a lot stronger. When you look at A, it's all non-polar. It's propane. It's a symmetrical structure, even in the geometric Bessemer geometry. It's all tetrahedral, and it's a non-polar. Only London dispersion force are involved in the intermolecular, so they don't interact as much as our polar. So the answer, because they don't interact much, they have a low boiling point. The answer is A.